Welcome to the Deep Dive, where we sift through the latest research and complex ideas to unearth those fundamental insights that truly make you well-informed. Today, we're plunging into a world you interact with constantly but rarely see, the bustling, sometimes chaotic realm of wireless communication. And believe it or not, we're facing a serious traffic problem right in the air around us.
It's a great analogy, actually. Imagine, if you will, rush hour on a digital highway. It's not cars bumper to bumper, but rather the invisible signals from your smartphone, your smart thermostat, your neighbor's Wi-Fi, maybe even that old cordless phone still kicking around. They're not vying for space on the same limited stretch of radio frequency.
Or like trying to have a conversation in a packed stadium, maybe, where everyone's shouting on the same channel.
Exactly, trying to be heard over the din. This fundamental challenge, this crowded finite resource, is precisely what we call spectrum scarcity in the wireless world. It's an invisible bottleneck that increasingly threatens to choke our hyper-connected future, where every device just expects seamless instant communication.
Okay, so that's the traffic jam, a very crowded digital highway. How do we build a smarter highway for our signals, then? This is where our deep dive truly opens up, because we're about to explore an incredibly clever concept designed specifically for this challenge. Cognitive radio, or CR?
Cognitive radio.
Think of it as a truly intelligent traffic cop, maybe. Not just directing cars, but dynamically rerouting and allocating lanes based on real-time conditions.
That's a good way to put it. The core premise of cognitive radio is quite elegant, really. It allows what we call secondary users, think your personal devices, maybe an emerging IoT network, to opportunistically jump onto and use licensed frequency bands only when the primary users are idle.
Primary users being the ones who actually own the license, like a TV broadcaster or maybe military radar.
Precisely. Those are the incumbents, the license holders.
Yeah.
So CR is about squeezing every last drop of efficiency out of the airways, turning unused capacity into valuable bandwidth.
Right, making use of those empty lanes on the highway.
And that opportunistic part is absolutely critical. Because if these secondary users are going to share the airwaves respectfully without causing disruptive interference, well, they need to be incredibly vigilant.
Vigilant, okay.
This brings us directly to the central challenge we're unpacking today. How do these smart radios actually know when a frequency is truly free? How do they detect, with, let's say, absolute certainty, the absence of the primary user's signal? This crucial foundational task is what the experts call spectrum sensing.
Spectrum sensing, the eyes and ears of cognitive radio, you could say.
It's fundamental.
But as you can probably already guess, it's far from as simple as just listening in. There's got to be a catch.
There usually is.
Our mission today is to unearth a critical, often hidden, and frankly, quite stubborn barrier that these sensing radios encounter. It's a fundamental limit known as the SNR Wall. We'll explore what causes it, why it's so problematic.
And then, perhaps most compellingly, we'll discover how strategic cooperation between these clever wireless devices can not only mitigate, but actually overcome this wall.
Even in tricky, noisy conditions.
Even then. It involves some really compelling insights about the fundamental physics of signal detection, the surprising and often frustrating impact of background noise.
And the power of collaboration, right. Teamwork for radios.
The undeniable transformative power of collaboration in our increasingly wireless world. Yes. Let's delve in and unpack this complex reality.
Okay, let's do it. Where do we start?
Well, to truly appreciate the implications of this SNR wall and why it poses such a formidable challenge, we first need to lay some essential groundwork. At the very heart of cognitive radio's promise, its ability to alleviate global spectrum scarcity, lies its core enabling task, spectrum sensing, or SS.
Got it, spectrum sensing.
The problem, as you alluded to earlier, is that the electromagnetic spectrum is a finite, universally shared resource. Yet historically, it's been heavily licensed to specific entities.
Right, those primary users.
Exactly. And this often leads to vast swaths of underutilized bandwidth. Think of it like a sprawling parking lot, with many reserved spots that sit empty for hours each day.
Which means all those precious frequencies, all that potential data highway, is just sitting idle for much of the time. That seems incredibly wasteful.
It is. And cognitive radio's monumental potential to alleviate this scarcity, to truly open up all that unused bandwidth, relies entirely on incredibly accurate and lightning-fast spectrum sensing.
So if a secondary user, say my smart doorbell trying to send a video feed, can't reliably tell if the primary user, maybe a critical security system, is actually present or not?
Then the entire system falls apart.
Yeah.
They might interfere with a licensed user, which is a major regulatory and operational no-no.
Big problem.
Or, conversely, they might needlessly sit idle when the channel is actually clear, wasting precious capacity. It's a delicate dance of detection.
Finding that balance.
Precisely. So the ultimate goal of spectrum sensing is for these secondary users to constantly and efficiently check the occupancy status of a primary channel. It's not enough to check once. They need to keep scanning. You can think of it quite literally as a driver endlessly, meticulously scanning a busy parking lot for that elusive empty spot.
Okay, constantly scanning. Makes sense. They need to know, in real time, if that space is truly available for them to occupy without blocking someone else.
And the faster and more reliably they can do this, the more efficient our wireless world becomes.
And when we talk about the initial approaches, the most common ways to do this spectrum sensing, I know various techniques exist, some quite complex.
Yes, many sophisticated techniques have been investigated over the years. Some require intricate knowledge of the primary user's signal structure. Others use complex statistical models.
But one method stands out for its elegant straightforwardness, its sheer simplicity, right? And that's energy detection.
Indeed. Energy detection, or ED, is a widely adopted technique, primarily because of its fundamental simplicity and low complexity. Unlike many other sensing methods, it has a huge practical advantage. It doesn't require any prior knowledge of the primary user's signal.
Ah, that's key. You don't need to know exactly what you're listening for, just if something's there beyond the usual background noise.
Exactly. You don't need to know the specific modulation scheme, the precise frequency, or what the signal looks like in terms of its unique signature. You just need to know if there's something detectable there, or if it's just background noise. This blind detection capability makes it incredibly versatile in real-world scenarios.
Where primary user characteristics might be unknown or change dynamically. Okay, so how does this conventional energy detection, CED, actually work conceptually?
It's pretty intuitive once you understand the core idea. At its heart, it measures the energy of a received signal. Think of it like measuring the sheer raw power or loudness of what's coming in from the airwaves, essentially. How much electrical energy the signal carries.
So it's calculating the amplitude squared of the received samples over a short period, like a sound engineer watching a level meter.
That's a perfect analogy. The higher the needle, the louder the sound, or in this case, the higher the energy. If that measured energy, that loudness, is above a certain predefined level, the detector decides a primary user is present and transmitting.
And if it's below that level?
It's assumed to be just random background noise, and the channel is considered free for opportunistic use by the secondary user.
Okay, measure energy compared to threshold. Seems straightforward, but you mentioned improvements.
Right. This seemingly straightforward CED can actually be made even more versatile, even improved upon. This is where the Generalized Energy Detector, or GED, comes into play.
Generalize. Okay, what's different?
It's an extension of CED, where that standard squaring operation, taking the amplitude to the power of 2, is replaced by an arbitrary positive power P.
Ah, P. So instead of always squaring, you could raise the signal amplitude to the power of 3 or 1.5 or something else.
Exactly. It introduces flexibility. So instead of always having P2, you could potentially use other positive values.
And this P factor sounds like it offers a significant degree of flexibility for optimization. The research suggests that choosing a suitable value of P could potentially refine the detector's performance.
Precisely. Depending on the specific environment or desired performance characteristics, you might find that a different value of P works better. It gives you a knob to tune, essentially. It's a tool for fine-tuning the detector's sensitivity and response under certain nuanced conditions.
But the core decision process is the same, compared to a threshold.
Yes. Regardless of the chosen p-value, the fundamental decision-making process for both CED and GED remains the same. It hinges on comparing the measured energy, or the powered amplitude, to a predefined threshold. This threshold is absolutely crucial for the detector's accuracy.
And ideally, that threshold is set based on the noise.
Ideally, yes. In a perfect world, this threshold would be perfectly determined by the true noise variance in the environment, essentially knowing the exact baseline level of background hum so you can reliably distinguish a faint signal from just random static.
Okay, so we have these clever radios trying to find open frequencies using energy detection, maybe the generalized version with this P factor. They measure signal strength, compare it against a threshold set by the noise level. Sounds logical. So what's the catch? What's the big hidden problem?
Here's where it truly gets captivating, because the ideal scenario we just described, well, it quickly bumps up against a messy reality. In a perfect theoretical world, we would know the true noise variance of the environment precisely. We'd know that background hum perfectly.
Right, if the background is perfectly steady and known.
Then you could theoretically sense even a primary user with a very low SNR, meaning a very weak signal, barely audible above the background. You could do it simply by increasing the sensing time, collecting more samples. We call the number of samples N.
So just listen longer. The longer you listen, the more data you get, and the more confident you become that a faint signal is really there.
Exactly. It's like trying to hear a faint whisper in a perfectly silent room. If you just listen for a second, you might miss it. But if you concentrate for a whole minute, you're much more confident if that whisper was real or just, your imagination playing tricks. The longer you listen, the clearer the signal becomes against a perfectly constant background.
Makes sense. But the real world isn't a perfectly silent room, is it?
Far from it. In practice, the real wireless world is far from ideal. That background hum, the noise variance, isn't static, it's not constant, it's not perfectly predictable. It varies with time as well as the location in subtle, complex ways.
How so? What causes that variation?
Oh, things like a microphone sensitivity slightly drifting, or the temperature in the room fluctuating, which affects electronics, or even other distant, unknown radio sources subtly contributing to the general electronic cacophony. This unpredictability, this unknown and fluctuating quality about the true noise variance is precisely what we call noise uncertainty, or NU.
Noise uncertainty. NU. Okay. It's the hidden, insidious foe that complicates everything. It makes our silent room more like a subtly humming server farm, maybe.
That's a good way to think about it, yeah.
Yeah.
We can't just assume the background hum of the wireless world is constant and perfectly known. It's constantly shifting, unpredictable. And the research defines this noise uncertainty using a factor, often denoted as gas wave, for the IF user.
And that's a ratio.
Essentially, yes. It's the ratio of the expected or estimated noise variance to the true noise variance. It's a measure of how much your estimate of the noise differs from the actual instantaneous reality. And critically, it's treated as a random variable because, as we said, the true noise is always fluctuating in the real world.
And how is this randomness modeled?
Often, its variation is modeled as uniformly distributed in decibels, dB, within some upper bound, let's call it Li.
Uniformly distributed. So within a certain range, say plus or minus a few dB, the actual noise level could be pretty much anything.
That's the idea. It makes it incredibly unpredictable and challenging to account for. Like trying to guess the exact strength of a background hum that's constantly fluctuating within a known maximum and minimum range. This basically quantifies the maximum deviation or uncertainty we can expect in our noise measurements. It defines the fuzziness of our noise floor.
Okay, so because of this fundamental, unavoidable noise uncertainty, this fuzziness, there's a truly counterintuitive and frustrating phenomenon that emerges, something the research calls the SNR Wall. What exactly is that?
It's a critical concept. It means that even if you extend the sensing time indefinitely, if you listen literally forever, making your number of samples and approach infinity, you cannot achieve a desired detection performance if the SNR falls below a certain specific value.
Wait, even if you listen forever, so increasing sensing time doesn't always help.
Not beyond a certain point. If the SNR is too low relative to the noise uncertainty, it's like hitting a hard, invisible ceiling. No matter how much processing power, how much time, or how many samples you throw at the problem, if the signal is too weak relative to the uncertainty in the noise, you simply cannot reliably distinguish it.
Wow, that's fundamental. It makes that simple energy detection seem less effective then, right? In the real world with NU.
It does. This is a critical and rather bleak implication for individual radios. It renders conventional energy detection, despite its simplicity, an inefficient sensing method in the presence of noise uncertainty. It's like your analogy of pushing a car uphill. No matter how much time you spend, how much effort you expend, if the slope is simply too steep.
Meaning the signal is too weak relative to the noise uncertainty.
You just won't make it to the top. The SNR wall is that fundamental steepness, a physical limit imposed by the unpredictable nature of noise. It's a barrier that cannot be overcome by simply listening longer or sampling more aggressively by a single device.
And you mentioned the P factor in the Generalized Energy Detector earlier. Does that help get over the wall?
That's a really crucial point. The SNR wall was initially derived for conventional energy detection, P2. But studies show that under the worst case of NU, the most challenging conditions, this fundamental SNR wall is actually independent of P for the Generalized Energy Detector.
So changing P doesn't help break through the wall itself.
Nope. That clever P factor, which might be useful for other things, simply doesn't help you overcome this fundamental SNR wall issue on its own. It's a deeper, more inherent physical barrier tied directly to the noise uncertainty itself, not the specific way you measure energy.
Okay, so this is a serious limitation for individual radios. If one device hits this wall, how do we ever achieve what you called unlimited reliability? Getting false alarms close to zero and detection probability close to one, even with lots of sensing time. How do we push past this limit?
That's the million-dollar question, isn't it? If one device, no matter how sophisticated, can't do it alone when facing this SNR wall due to noise uncertainty, what's the next logical step?
Teamwork.
Exactly. Cooperation.
Okay, so the next step, the way around this SNR wall, is cooperative spectrum sensing, or CSS. Makes intuitive sense. Team up.
It's exactly what it sounds like.
Yeah.
Multiple secondary users working together, pooling their observations to gain a clearer, more reliable picture of the spectrum. It's the ultimate team sport for radios, designed to overcome those individual limitations.
So why is cooperation so essential here? What are the limitations it overcomes?
Well, let's explore that, because individual secondary users in a real-world network face a lot of variability. Their signal-to-noise ratios, their SNRs can differ wildly.
Depending on where they are, right? Distance, buildings in the way.
Exactly. Physical distance from the primary user, the specific propagation path the signal takes blocked by a building, bouncing off metal, or even just local interference near one user but not another. And crucially, their noise uncertainties their NUs can also vary.
Why would the uncertainty vary?
Due to things like subtle calibration errors in their internal circuits, minor thermal noise fluctuations in their components as temperature changes, or even changes in the gain of their low noise amplifiers. Tiny variations, device to device.
So relying on just one secondary user in such dynamic, unpredictable environments is just too unreliable.
Precisely. It's too fragile to build robust cognitive radio systems on.
So instead of going it alone, M number of secondary users decide to cooperate. How does that work mechanically?
Each secondary user still takes its own N samples during an observation interval. They're essentially listening to the channel independently from their unique vantage point. Think of it like multiple scouts, each positioned at a different angle, reporting back what they see or hear to a central command.
Okay, and the signal they receive, how is that modeled?
In our system model for this deep dive, we consider the received signal at each ith secondary user, let's call it YMN. This signal, at any given moment N, consists of either just noise or that background hum we discussed.
That's hypothesis H0, channel free.
Correct. H0 means the channel is free. Or the signal, yin, contains both the primary user's signal, sin, plus noise, win. That's hypothesis H1, channel occupied.
And the noise is assumed to be AWGN.
Yes. We simplify this complex real-world noise by assuming additive white Gaussian noise, AWGN. It's a common and robust mathematical model. While it's a simplification, it allows for powerful analytical insights and gives a strong foundation for understanding the core challenges without getting bogged down initially.
And each of these cooperating users uses that generalized energy detector, calculating their own statistic T based on the signal raised to the power P.
That's right. Each one computes its own local decision statistic, T, based on yin. But here's where the cooperation truly begins. Instead of making an immediate local decision and acting on it.
They share their findings somehow.
Exactly. They prepare to share their findings or their raw data with a central entity.
Before we get to the sharing, let's quickly recap the performance metrics. Still, probability of false alarm and probability of detection.
Yes, those are the core metrics. First, the probability of false alarm, PA-phi, for the ith user. That's the chance of detecting a primary user when none is actually there.
A missed opportunity to use a free channel.
Right. And then the probability of detection, PDI. That's the chance of correctly detecting a primary user when one is actually present.
Which is crucial for avoiding interference, protecting the licensed user.
Absolutely critical. And these probabilities, PI and PDI, are critically dependent on that decision threshold.
The threshold set based on noise variance, trying to find that sweet spot between missing opportunities and causing interference.
Precisely. It's a constant optimization challenge in real time.
And you mentioned the central limit theorem earlier. That helps here too.
Thankfully, yes. For a sufficiently large number of samples, N, the decision statistic T that each radio generates, can be very accurately modeled by a Gaussian or bell curve distribution. This is a profound simplification because it makes the analysis much more tractable. We can describe its behavior simply by its mean and variance.
But we still have that pesky noise uncertainty, the random variable. How does that factor in?
Good point. We can't forget that. So to get a realistic picture, the average probabilities, we denote them, P phi and PD, are calculated by averaging the instantaneous PFI and PDI over the probability density function of PD. It's about incorporating that real-world unpredictability into the model, ensuring our calculations are robust.
Okay, so now the cooperation. They pool their data at a fusion center, FC.
Right. When these secondary users truly cooperate, pooling their data or decisions at a central fusion center, we get combined average probabilities for the whole system. QF for false alarm and QD for detection.
And the goal is still unlimited reliability. QF goes to 0, QAD goes to 1, as sensing time n gets large.
That's the dream scenario, and the SNR wall is precisely what prevents this from happening below a certain SNR if noise uncertainty is present for a single user. And that's what we're aiming to break through with this ingenious concept of cooperation.
All right, let's get into the nitty-gritty of how these cooperating devices actually combine their information. We'll start with hard decision combining. What does that involve?
Okay, hard decision combining. This is where each secondary user makes its own individual on-off decision first. Basically, a simple binary choice, channel occupied or channel free.
Like a yes or no vote.
Exactly. They then send this simple binary result, just one bit of information, to the fusion center. The FAC then applies a specific combining rule to all these votes to make the final system-wide decision. It's like a democratic process where each radio gets one vote.
Okay, and what are the common rules?
Let's look at the first and arguably most permissive or cautious rule, the OR combining rule.
Or rule, how does that work?
Under the OR rule, the logic is incredibly straightforward and quite conservative, you might say. The fusion center declares the primary user active if at least one of the cooperating secondary users reports the channel as occupied.
So if anyone shouts danger, everyone reacts, even if the others didn't spot it.
That's the idea. Think of a team of lookout scouts. If any one of them sees something suspicious, the alarm is raised. You don't wait for everyone to agree. This rule prioritizes avoiding interference with the primary user above all else. It leans heavily on the side of caution.
Okay, prioritizes protection. What does this mean for the SNR wall? Can the OR rule help break through it?
Yes, and the implications are truly fascinating. It reveals a powerful leverage of diversity in the network. Let's consider a simple scenario with just two cooperating secondary users, M2. To achieve that coveted unlimited reliability, QF approaching 0 and QED approaching 1, the decision threshold used at the fusion center must satisfy certain conditions. These conditions relate the threshold to the noise uncertainty, LI, and the SNR at each individual secondary user.
And what's the key insight here for the RR rule?
Here's the truly powerful insight. The mathematical models show that for the entire cooperative system to succeed and push past the SNR wall, you only need one of those cooperating devices to meet its individual signal strength requirement relative to its own noise uncertainty.
Only one. So if one user has a really good signal, it can compensate for another user having a bad one.
Essentially, yes, for the OR rule's goal. For instance, say you have two users. User 1 has a noise uncertainty L1 of 1 dB, and user 2 has L2 of 0.5 dB. The derived condition for the SNR wall might require either user 1's SNR to be above, say, 0.46, or user 2's SNR to be above, say, 0.37. If either one of those conditions is met, the whole system achieves unlimited reliability with the OR rule.
Wow. So one strong link can pull the entire system past the wall. That's powerful, like a relay race where one fast runner makes up for a slower teammate.
It's a great analogy. That single strong observation validated by the OR rule's logic is enough. And crucially, the research confirms that for the OR rule, this ability to break through the SNR wall is still independent of P. That arbitrary power factor doesn't change this fundamental limit.
Still independent of P. Okay, and this extends to more than two users.
Seamlessly. If you have M cooperating secondary users, as long as any one among those M users can meet its specific SNR requirement relative to its own noise uncertainty, that's its wall value, the entire system can achieve unlimited reliability using the OR rule.
That seems really useful in real networks where conditions vary a lot. What about the case where all users have the same conditions?
Yes, there's a special case. If all the cooperating secondary users happen to have the exact same SNRs and the same noise uncertainties, L, the SNR wall simplifies into a neat formula. It involves the maximum and minimum noise uncertainty bounds across the group. It provides a baseline understanding for more uniform environments.
Okay, that's the OR rule. What's next? The opposite.
Pretty much. Let's flip that coin and look at the A and D combining rule, which is much stricter and operates on a very different philosophy.
And D rule. Sounds like everyone has to agree.
Exactly. Here, the logic is far more stringent. The fusion center declares the channel occupied only when all the cooperating secondary users report the primary user channel as occupied.
It's like a high-security protocol. Every single guard must confirm all clear before you proceed.
Perfect analogy. If even one person or sensor says there's a primary user or simply reports channel occupied based on their local decision, the A&D rule logic leads the SAC to consider the channel busy overall for the purpose of achieving Q at 1. However, for achieving Q2O, all users must report channel free. It's a bit complex. The core idea is unanimity is required for certain outcomes. The paper focuses on the SNR Wall condition for achieving both QS and QD1, and for that to happen.
What are the implications for the SNR wall with A&D?
It reveals an inherent demand for widespread strength, again, considering two cooperating users, M2, to achieve unlimited reliability, both QS and QA1. Both individual secondary users must meet or exceed their respective SNR wall values.
Ah, so no compensation here. If one user is below its wall, the whole system fails for the A&D rule, even if the other user is really strong.
That's the crucial distinction. Unlike the OR rule, here, all cooperating SUs must individually satisfy their SNR wall conditions. There's no ability for one strong SU to completely pull up a weaker one in this context. It's like a chain that's strength is determined by its weakest link when using the AD rule for achieving that perfect reliability.
And that extends to M users, too. All M must meet their walls.
Yes. For M cooperating secondary users, all of their individual SNRs must be greater than or equal to their respective SNR walls to guarantee unlimited reliability with the A&D rule.
And the special case with identical users.
Similar to the OR rule, if all secondary users have the same SNR in U, the SNR wall follows a similar formula structure. But there's a subtle yet critical difference in how the maximum L plus and minimum L uncertainty values are defined within that formula, reflecting the different logic of AND versus OR.
Okay, OR is anyone, ND is all. Is there something in between?
Absolutely. That brings us to the most general and arguably the most flexible case, the K out of M combining rule.
K out of M, like a majority vote or a quorum.
Exactly. This is the flexible option, offering a continuum between the two extremes we just discussed. Under this rule, the fusion center declares the channel occupied when K out of the total of M cooperating secondary users report the primary user channel as occupied.
So you can choose K. If you have M5 users, you could require K3 to agree.
Precisely. You can set K to be anything from 1, which is just the OR rule, up to M, which is the AND rule. This flexibility allows network designers to precisely tailor the detection strategy to specific application requirements, balancing false alarms against missed detections based on the system's priorities.
How does this affect the SNR wall? Let's take an example, maybe M3 users and K2. So 2 out of 3 need to agree.
Good example. Let's say we have M3, K2, and they have different noise uncertainties, L11 dB, L2.7 dB, L3.5 dB. The analysis derives individual SNR wall values for each, say L1 wall 0.38, L1 wall 0.32, L3 wall 0.28. Now, for the system to achieve unlimited reliability with this K2 rule, the condition is that any K conditions must be satisfied.
So in this case, any 2 of the 3 users must have their SNR meet or exceed their respective wall value.
Exactly. Even if one user is below its wall, say 1 NOI 0.2, the system can still achieve unlimited reliability if the other 2 meet their conditions. Is 2.32 and 2.3 or 0.2.
That really shows the flexibility. It offers a balance between the strictness of A&D and the leniency of OR.
It does. It allows for a robust, flexible approach to collective decision-making, tunable via the choice of K.
So comparing these hard combining rules, OR, A&D, K out of M, what are the key takeaways about their SNR walls?
Some clear patterns emerge when you compare them, drawing insights from the research like in Table I of the source paper. The OR rule often results in higher individual SNR wall values. Paradoxically, each user needs a better raw SNR on its own to hit its OR rule wall.
But it's more forgiving overall because only one needs to make it.
Correct. It's more forgiving for the system because only one SU actually needs to meet its condition. It prioritizes PU protection. In stark contrast, the A&D rule tends to have the smallest individual SNR wall values. Theoretically, each user doesn't need to be quite as strong individually.
But the catch is all of them must meet that lower bar.
Exactly. It demands that all SUs satisfy their conditions. A very high bar for collective performance, despite the lower individual thresholds. And the K out of M rule, as expected, lies between OR R and A and D. It requires KSUs to satisfy their conditions, offering that tunable trade-off.
And the independence from P holds for all of them.
Yes. What's consistently reinforced across all these hard decision combining rules is that the SNR wall is consistently independent of the value of P. That generalized energy detector parameter simply doesn't shift this fundamental limit for hard combining.
Okay, hard decisions are like votes. What about sharing more information? That brings us to soft decision combining, right?
Exactly. This method offers a fundamentally different approach, often more powerful, because it leverages more of the raw information gathered by each secondary user.
So how does it work? They don't just send a yes or no.
No. In soft decision combining, the secondary users don't make individual on-off decisions at all. Instead, they send their raw decision statistics. Think of these as their continuous energy measurements, the actual numerical values representing the signal strength they detected, directly to the fusion center.
So they send the actual measurement, not just a thresholded result.
Precisely. The FEC then intelligently combines these richer statistics. A common and effective method for this is called equal gain combining, or EGC. With EGC, the FEC simply adds these continuous measurements together to form a grand, collective total energy measure.
Like gathering all the individual sound level readings from different spots and summing them up, instead of just getting a thumbs up or thumbs down from each meter, you keep more detail.
Perfectly put. You retain much more information about the signal's strength and variability across the network.
Does this combined statistics still follow a nice distribution?
Yes, conveniently, this combined decision statistic, let's call it T, the sum of the individual T's, also follows a Gaussian distribution, thanks again to the central limit theorem, assuming enough samples n. This mathematical consistency is incredibly valuable. It means we can still describe its behavior simply and predictably with its own new collective mean and variance.
So what happens to the SNR wall with soft combining? How is it derived?
When the research delves into deriving the SNR wall for soft combining, often starting with a simplified case, say M2 users, and setting P2 for mathematical clarity, it reveals something truly profound. It shows that to achieve unlimited reliability, it's not about each user hitting an individual target, but about their combined strength.
Combined strength, how so?
The key finding is that the sum of the individual SNRs from the cooperating users must be greater than or equal to a value determined by their respective noise uncertainties, L1, L2, etc. The mathematical condition looks something like SUF1 plus 200, some function of L1 and L2. The equality gives the SNR wall.
So it's the sum of the SNRs O1 plus 2 that matters, not O1 and duo individually needing to cross some threshold.
Exactly. It's about the collective signal strength, overcoming the collective impact of noise uncertainty across the cooperating users. If one device has a weaker signal, low way, another with a stronger signal, high way, can compensate, as long as their combined effect, their sum, is sufficient.
That seems really significant. What are the big conclusions from this?
It leads to some truly powerful and even surprising conclusions. First, and perhaps most importantly, it confirms our understanding of the wall's origin. If there's no noise uncertainty at any cooperating user, L1, L2, 0, their noise estimates are perfect, then unlimited reliability is achievable at any SNR greater than 0.
So the wall vanishes without NU. It really proves NU is the root cause.
Fundamentally, yes, the SNR wall is inextricably tied to noise uncertainty.
Okay, what else? You mentioned something surprising.
Yes, here's a particularly interesting finding, one that might initially seem counterintuitive. If all cooperating secondary users have the same noise uncertainty, L1, L2L, and the same SNRs, the analysis shows there is effectively no improvement in the SNR wall value compared to using a single, non-cooperating secondary user with that same L and I.
Wait, no improvement if everyone's the same. Why cooperate then?
It's a great question. It highlights that cooperation's true power, especially with soft combining, lies in leveraging diversity, not uniformity. If all radios are experiencing the exact same conditions and uncertainties, just pooling their identical limited data doesn't provide a significant advantage against that fundamental noise uncertainty limit.
So the real advantage of soft combining comes when conditions differ across the users.
Precisely. What's truly fascinating here, and a major aha moment from the research, is that the biggest benefit of soft combining comes when SNRs vary among the secondary users. This is because the SNR wall is determined by the combined SNR. It opens up a world of possibilities for network optimization and resilience.
Can you give an example?
Sure. Think about it. Even if one secondary user has a very low SNR, maybe it's far from the primary user, or stuck in a noisy basement, the system can still achieve unlimited reliability. if another cooperating secondary user has a sufficiently high SNR to compensate for its partner's weakness.
So if the combined wall requires a total SNR of, say, zero point 0.7.
Right, that could be met if user 1 has 1.1, really
Yeah.
poor, but user 2 is comping an R best quite 6, quite good. Their sum is zero point 0.7 meeting the requirement. The paper gives a specific example, L11 dB. L2.5 dB requires a combined SNR of 0.6954. This can be met by GIL 1.3954 and GIL 2.3. User 2 is weaker, but user 1 compensates.
That is incredible. It's like a team effort where different skills contribute. One strong player can carry the team over the threshold.
Exactly. This ability to aggregate and compensate is the real magic of soft combining, making it incredibly resilient in heterogeneous wireless environments where signal strengths naturally vary.
And this extends to M users as well. The sum of all MSNRs needs to meet the combined wall.
Yes, the principle extends naturally. The sum of their individual SNRs must collectively meet or exceed the combined SNR wall value, which depends on all the lies. It truly highlights that the collective sum of individual capabilities can overcome limitations that would stop any single participant cold.
And the P factor independence, does that still hold for soft combining?
Yes, it does. The paper we're discussing explicitly demonstrates through rigorous simulations that the SNR wall for soft combining is also independent of the value of P. While the initial mathematical derivation might have assumed P2 for simplicity, the principle holds more generally. Changing P doesn't shift that invisible wall.
So whether you square the amplitude, P2, or cube it, P3, the fundamental combined SNR required to beat the wall, given the noise uncertainties, stays the same.
Correct. The wall itself is a property of the noise uncertainty and the combined signal strength, not the specific exponent used in the energy calculation.
Okay, this theory of cooperation overcoming the SNR wall, especially the flexibility soft combining, sounds great. But how do we know it actually works? How was it tested?
Excellent question. Theory is fascinating, but robust scientific research always puts its findings to the most rigorous test. The paper confirms its theoretical findings using extensive Monte Carlo MC simulations.
Monte Carlo, that involves running lots of simulations, right? Like digital experiments.
Exactly. It involves generating a vast number of simulated scenarios, essentially, running countless digital experiments under the specified conditions, and then statistically averaging the results. The goal was to see if these simulated outcomes precisely matched the mathematical predictions derived from the theory, providing confidence in the analytical models.
What kind of results did they look at?
They used several tools. For instance, receiver operating characteristic, ROC plots. These are standard in signal detection. They visually show the trade-off between the combined probability of false alarm, QF, and the combined probability of detection, QD, as you vary the decision threshold.
And did the simulations match the theory?
Perfectly. The crucial finding was that the theoretical curves derived from the math perfectly overlapped with the simulation results. This held true for both hard and soft combining and across different values of P and different sample sizes, N. This visual congruence is strong validation. It means the math accurately reflects what happens.
What else did they plot? You mentioned verifying the SNR wall itself.
Yes, they also utilized threshold versus probability plots. These were especially crucial for verifying the analytical expressions for the SNR wall directly. Here's how. They set the number of samples, N, to an extremely large value, 106, in their simulations, effectively mimicking listening for a very, very long time.
Approaching that infinite sensing time limit.
Exactly. This allowed them to clearly observe if, beyond a specific threshold, the probability of false alarm, QF, truly dropped to 0, and the probability of detection, QD, rose to 1.
Okay.
Precisely when the derived SNR wall conditions, based on the chosen Guy and Lie values, were met.
So they could visually see the system achieving unlimited reliability right at the predicted SNR wall threshold.
That's right. It empirically demonstrated that crossing that specific SNR wall value allows you to find a threshold that yields that desired perfect performance, validating the whole concept.
Can we walk through some specific simulation examples, maybe starting with hard combining?
Sure, let's visualize how these concepts played out, starting with hard combining, where they typically set P to 2 for these plots. Looking at the OR rule simulation, Figure 2 in the paper showed this powerfully. They set it up so one secondary user was operating below its individual SNR wall, 1.2 maybe.
So that user alone couldn't guarantee reliability.
Correct. But the other cooperating user did meet its individual SNR wall condition, SNR 0.3676, matching the calculated wall. And the simulation showed that unlimited reliability for the entire system was still achieved thanks to the OR rule. The plot showed QF going to 0 and QO going to 1 at a specific threshold, 1.26.
Demonstrating that OR rule forgiveness, the strongest link prevails. What about the AND rule?
For the AND rule simulation, figure 3, the results powerfully demonstrated its stricter requirement. They set the SNRs so that both secondary users met their respective lower SNR walls. Only then did the simulation show unlimited reliability was possible, converging at a threshold of 1.11, visually reinforcing that all participants must individually perform for AND.
Makes sense. And the K out of M rule? The example was M3, K2.
Yes, figure 4 showed the K out of M simulation, M3, K2. They again set it up so one user was below its wall, DL 1.2, but the other two did meet their individual walls, DFO 0.32380, NEWO 0.2836. Sans K2, the condition was met. And indeed, the simulation confirmed the system still achieved unlimited reliability at 1.16, showcasing the flexibility of requiring only a subset to succeed.
Okay, those hard combining results clearly match the theory. What about soft combining? Did the simulations confirm the combined SNR idea?
Absolutely. The soft combining simulations truly highlighted the power of aggregation. For two cooperating users, M2, figure 5, they specifically set the individual SNRs, YAD1 0.3, JEDISHU 0.3954, such that their sum, 0.6954, precisely met the calculated combined SNR wall condition for their given noise uncertainties, L1 1 dB, L2 1.5 dB.
So one user was okay, the other a bit weaker, but their total was just enough.
Exactly. And the simulation results undeniably showed unlimited reliability being achieved at a threshold of 1.2. This graphically confirmed that powerful idea. Lower SNR at one SU can be compensated by higher SNR at another in soft combining. It's the collective strength that matters.
Fantastic validation. And did they also confirm the independence of P for soft combining?
Yes, that was another crucial check, figure 6. They repeated the end of 2 soft combining simulation, but this time using a different p-value, P3 instead of P2. Critically, they kept the same total combined SNR, got a 1 plus P2, but previously achieved the wall.
And the result?
The system still yielded unlimited reliability. Q went to 0, QD went to 1. This strongly reinforced that the SNR wall itself is not dependent on the P parameter for soft combining either. The threshold simply shifted to 1.72 in this case, as expected, because P affects the statistics distribution. But the fundamental ability to achieve unlimited reliability at that combined SNR remained unchanged.
So across the board, the simulations rigorously backed up the theoretical findings about cooperation, the different combining roles, and the nature of the SNR wall.
Exactly. It provides strong confidence in these models.
Now, you mentioned earlier that this research focused on a specific type of noise channel, AWGN. What was excluded?
Right, it's important to note the scope. The paper consciously excluded the complexities of what are known as fading channels. Fading is where the signal strength fluctuates dramatically due to the environment reflections, obstructions, movement. Think of your cell signal dropping in a tunnel or inside a concrete building.
Or Wi-Fi being patchy in different rooms.
Precisely. Those effects add significant randomness and complexity to the received signal strength itself, beyond just the noise floor uncertainty. The researchers explicitly state that including fading models would considerably increase the mathematical complexity, involving many more tricky integrals and potentially obscuring the fundamental insights about the SNR wall due to NU alone.
So they simplified the channel model using AWGN to isolate and clearly understand the impact of noise uncertainty and cooperation on the SNR wall itself.
Exactly. It's a common scientific approach. Isolate variables to understand their core effects. It doesn't diminish the findings about NU and the SNR wall and AWGN. It simply defines their scope. And of course, it highlights a really important area for future research. Extending these cooperative sensing analyses to more complex and realistic fading environments. How do these SNR walls behave then? How do the benefits of cooperation change? That's a whole other deep dive.
Understood. It sets the stage for more work, but the fundamental insights about NU, the wall, and cooperation are clearly established here. Hashtag tagged, hashtag to hard beaching.
So what does this all mean? Conclusion and provocative thought.
So let's try and wrap this up. What does this all mean for us and for the future of our increasingly connected world? We've just navigated a truly complex landscape, haven't we? We've unpacked cognitive radio, spectrum sensing, the nitty-gritty of noise uncertainty, and confronted that fundamental invisible barrier, the SNR wall.
Yeah, that SNR wall is a key concept, the hard limit.
It is. But the encouraging part, the main story really, is how cooperative spectrum sensing offers these incredibly powerful and ingenious ways to navigate and even overcome this wall. whether using hard or soft decision combining.
Making our wireless world potentially much more efficient and reliable.
Ultimately, yes, that's the goal.
So maybe we can quickly recap the key takeaways for, some listening. First, that noise uncertainty is not just theory. It's real, it's inherent, it affects every wireless system out there. Absolutely, it's an unavoidable challenge. Second, the SNR wall is a direct consequence of that uncertainty. It defines a hard, physical limit for detection performance if you don't manage NEU intelligently, a fundamental roadblock for single devices.
But takeaway 3, cooperation is the game changer.
It really is. It allows wireless devices to leverage the diversity in their conditions. Some have better signal, some worse. Together, they can achieve reliability that individuals simply cannot. Teamwork for radios.
And the type of cooperation matters. Takeaway 4, hard combining, OAM, AD, KILO-M, is like voting. It determines how many users need to be strong.
Right. While soft combining, like EGC, allows for a true collective strength. High SNR users can actually compensate for low SNR users, pooling their richer information. It's about the sum total.
And finally, that P factor in the Generalized Energy Detector. Useful for other things, maybe, but it doesn't move the SNR wall itself.
Correct. Surprisingly, that fundamental limit seems independent of P for both hard and soft combining. Based on this work, it's tied more deeply to the noise uncertainty and the SNR levels.
Okay, so as a final provocative thought to leave everyone mulling over, think about the sheer scale of connection around us. Billions of devices.
Phones, smart homes, IoT sensors, industrial controls, critical infrastructure.
They all rely on efficient, interference-free communication. Understanding concepts like this SNR wall and cooperative sensing isn't just academic jargon, is it?
Not at all. It's about fundamentally pushing the boundaries of what's possible in a world absolutely saturated with wireless signals.
How might these findings actually influence the design of the next generation of wireless networks, 6G and beyond?
Well, think about dense urban environments, canyons of buildings, signals bouncing everywhere, lots of interference, or critical communications emergency services, vehicle safety where reliability is non-negotiable. Cooperative strategies, informed by understanding these SNR walls, could be key to creating more robust, self-healing networks that adapt to those harsh conditions.
And looking even further ahead, what about truly autonomous vehicles? They need instant, hyper-reliable data. Milliseconds count.
Or fully immersive virtual and augmented reality. That demands massive, consistent bandwidth with almost zero perceived latency. What further complexities will those frontiers introduce? Will they require even more ingenious cooperative solutions to navigate the invisible barriers, the noise, the interference, the fighting?
It sounds like the challenge is constantly evolving, demanding ever more cleverness from our smart radios and the networks they form.
It certainly is. It's a fascinating and critical area of research, constantly pushing the limits of physics and engineering to keep our connected world running smoothly.
Definitely something to think about. Thanks for breaking down such a complex topic.
My pleasure. It's a crucial stuff.
And thank you for joining us on the Deep Dive. We'll be back soon to explore another fascinating corner of research.